So what I talk today is negative mobility in interacting particle systems. So let us see what exactly I mean by negative response or negative mobility. So basically, you take a system, open system, and you put some voltage, and then if you put some voltage or some potential, then the current will flow in the direction of the gradient. I mean that we know, and then already some current is flowing, and if you increase the potential again, you get more current. That's what intuitively what it says. So basically, what you have is that current versus bias is always an increasing function. Okay, so ohmic conductor or semiconductor, this is the normal situation. But what I'm going to say today is that both these expectations, that you increase a potential, right? I mean, if you have a potential, current flows in this direction instead of current can flow uphill. It can happen in non-equilibrium. Other thing is that some current is flowing in the system. You increase the potential, the current actually can decrease. And I will try to tell you in general in what kind of situation it can happen, and I try to convince you on the mechanism. And this is what will happen. Current has a kind of bias, it increases, but after that it decreases. So if it is electrical current, you can see that resistance in this region is negative. Okay, so that's what called negative response, or if the particle current, this is called negative mobility. I will talk about that. So what I intend to talk about is negative response and the mechanism of negative response in non-equilibrium systems. So before that, so let us start. Why do you expect these two things? Put a potential, current flows in downhill. Why? I mean, and why? What is the basis of that? So let us say that in equilibrium, you have current average is 0, but then current is a microscopic quantity. There could be microscopic fluctuations, but if you take a square, J square average, even in equilibrium, there is some finite value. There are microscopic fluctuations. So this you can think like a paramagnet, where M average is 0, but M square average is finite. Okay. So now the description of a paramagnet can be, you can write like a partition function, like Z to the power M. Qm is the partition function for the magnetism, and Z is e to the power minus beta h. So this is basically like, if you put a field, then e to the power minus beta h or h, you can put it here. And then if you calculate M average, these are standard relations, and you know that dm by dh is M square average minus M average square, which you call susceptibility. And this quantity is positive because M average minus M average, M minus M average whole square average. So this is positive, and dm by dh has to be positive. So if you put a small field, so basically you expand it like around zero field. So this is 0 plus h dm by dh, but dm by dh is just positive. So this is just h times M average is 0. So this is just M square average. Okay. So what it means that if you if you take a paramagnet, put a little bit of field, the rest what you get is what magnetization you get is proportional to field and proportional to the M square. Okay. So that's the positive one. And so you can take the same analogy, saying that J of epsilon is J0, in equilibrium is the J equal to 0 state, and if you do that at epsilon equal to 0, so what, right, epsilon equal to 0, J0 equal to 0, so dJ by d epsilon is just J square average minus J average square, which is greater than 0, and the current actually will be epsilon times J square average at equilibrium. So if you put a small field, the current what you get is proportional to the field, and so if the field, this is positive, so if the direction is, this is positive, then the current is positive. So the direction of current is the direction of the field, and response is always positive. So if you increase, so this is the understanding. So how can you go beyond that? So what you say that before going that, let us see that what we mean by current and how to calculate current. So take a single random walker on a lattice, and I call it A0 goes to 0A, P and Q are this is a biased walk, and I have to define a bias. So bias, if you say that in a space, if you have a potential like that, if you have a gradient, you can see that if a particle goes from here to here, and if you want to do a Monte Carlo, because it's a lower energy, the rate is 1. If you go towards this, the rate is e to the power minus epsilon, because this height is epsilon. Okay. So these are the rates. So if you compare P equal to 1 and Q equal to e to the power minus epsilon, you can call it epsilon is the field here, that's the gradient. So log P by Q is your epsilon, that's your field. And the current in this one, because the state is just homogeneous, like particle can be anywhere, all states are equally likely, and the current is simply just number of right moves minus left moves. It's just P minus Q, simple. Okay. And if you plot it current versus epsilon, this goes positive. That's just kind of to know. So now let us take many workers. Many workers. So in this case, again, the state is homogeneous, it's on a ring. So particles move towards right, the probability that it moves to the right minus left, P minus Q, it is P minus Q is positive, and dj by d epsilon, like the previous case, it's still positive. Let's go further. You take many occur, but no exclusion. Okay. So let us say that lattice, it's not that a site can occupy one particle, it can have many particles. So in that case, you have a dynamics. You say that particle can go to right or left. That is decided by P and Q. So the right moving is P times some UN. UN is basically rate, which depends on the number of particles here. Some function. I don't need to know the function. And to the right it is P, and to the left it is Q. For example, from this side of 4 particles, particle goes to the right with P times U4. This, and from here I go to the right go to the right with P times U2, and left with Q times U2. So that's the model. And in this case, this is called a zero range process, and the model is exactly solvable. And you have a steady state weight. It's a product measure, and some exact results are there. And if you want to calculate current, it's a very simple calculations. You calculate the current. This is just P minus Q times Z, because this system is a particle conservation, and Z is the fugacity. Okay, and the density as a fugacity, you know that this is an increasing function. So this Z is an increasing function. So this is positive anyway, and dj by d epsilon is still greater than 0. Okay. Let's go further. So it is very difficult to get. You can see that it doesn't matter how you construct. It's very difficult to get. So 2 species exclusion process, the one he said. So it's like you have 2 particles A and B on a ring. They're moving, and what I say is that let us say only A is biased, but B is not biased, and there is also exchange rate with alpha. Okay. Then here only A particles are biased, and if you want to calculate, I will not show you numerical results. Just tells us that current is still positive. dj by d epsilon is positive. You have positive response. Now we put an additional field on B. Let us say there is psi and phi. Instead of psi, you call it phi. So there is a B. Let us move to right, but with extra. There is extra potential which is different from A. This is a different field. So in this case, this is log phi by psi. That's a new field. And for a given fixed field and alpha, for any fixed field, you can actually show numerically that this is the one. So this is still positive. You don't do much. So that's the first model where you can see negative response and see this is the model. So we must say that additional interaction among A and B particles. What we say that this was earlier, this this exchange and this bias move of A, this was there. Now B particle can move to right depending on what is here. The rate, it actually depends on what is here. Tau can be 0, 1, or A or B. 0 means vacant, or B particle. So depending on that, there is a rate here. So similarly, when it moves to left, it depends on what is the particle here. So that's what we do. And what I choose is that you could choose whatever rates. I choose R0, means when this is 0, that is a B is isolated B. So that is W, and all other rates, there are 6 such rates, all of them are 1 minus W. So you can see that only isolated B particles are biased. So if B particle is an isolation, it is biased, but fixed bias. And anyway, A particles are always biased. Okay, so I want to find current in terms of this epsilon, and then find that the current is actually positive here. Okay, so this is for some fixed parameters. So there are 2 conserved quantities, density of A, density of B, and the parameter which is alpha, this exchange rate, and W which comes from here, B, this is fixed, these are fixed. And what you find is that for fixed, and B is positive, I take W equal to 0.9. So W equal to 0.9 means left is 1 minus 0. B particle is biased, but it is biased towards right. So both the particles are biased toward right. It's not that I'm compensating one, but you still get a negative response. Okay, so current goes and goes down. If you increase your potential epsilon, that's the only parameter you can change now. You can see that there is a negative response, and the response depends on how many B particles are there. So it's a low density, you see this response. In high density, you don't see it. So the negative differential mobility for JA and JB, and of course for total current J equal to JL plus JB also will show a negative response here. So this is the first example, numerical. So now try to say, why does this negative response occur? To understand that, what we try to do is that we try to find out other observables. So the current is number of A particles which is going to the right with respect to number of particles which is going to the left. This is the difference. But there is also some quantity, the total number of jumps which can occur, NR plus NL, right? I mean total number of jumps, I call it number of jumps for A and B particles. total number of jumps. That's called traffic. What is the activity for the traffic? Okay. So we also measure how many jumps actually occurring in the system in the steady state, and you find out in epsilon this is the behavior. So density equal to rho b equal to 0.1, rho b equal to 0.5. These are the behavior. So if you try to compare, you see that the what you call traffic, the total number of jumps of A actually has a relation. You can see that this red one matches with this red one. So if you want to calculate, because A is biased, you want to see how A particle moves. So the traffic of B actually relates to the current of A. So if the traffic of B is this one, current of A is exactly similar. So traffic of B is this one, current of A is similar, but traffic of A doesn't have any correlation. So it seems that there are interacting particles. The one particle is biased, the other one is not biased, but the traffic of that is actually decreasing somehow. And just because of interaction, this is actually putting negative response on the driven degrees. So the current of A particle, which is the driven sector, follows the traffic of B. Okay, so that looks like a conjecture here, one model. So we try to prove this, and we want to say that this is actually the mechanism in interacting particle system. Okay, so the conjecture is that, particle current in a driven many particle system might show a non-monotonic behavior if some modes, which are not driven by this external field, slow down with increasing driving. So if this is what happens, then it can actually show negative response, and that's so this is many particles. Current has, in interacting particle system, there are many degrees of many modes which carry current. One is coupled to the other. So you slow down one mode, and non-driven mode that can create actually current in the other one. Okay, so now if that is the case, then we go back to the this two-species exclusion model, and there was this, this was not biased. But what if you put explicit dependence on the bias on this? They are diffusing, but explicit bias. And in this case, we show that actually you get a negative response here. Okay. I'll take 1 minute. So then what we do is that, the simplest scenario, we have a lot of exactly solvable models in this case. This scenario which I propose can be explicitly shown in many, many examples. So the simplest one is just take 2 random markers, okay? And there is no exchange. It's a very simple exercise. I, probably ask the student to do it. So basically, there are only 2 random markers, and there is just this dynamics. And the model is non-trivial. I mean, if you have an exact solution, you have a matrix algebra. And this one, actually, you can show the current in this system just with 2 random markers, no exchange, can show a negative response. Okay. So we have other models. I wanted to show how, so basically, one point is that what goes wrong with the response formula. Okay, so the answer is actually the response formula, which was there earlier. That's for equilibrium. There is a cross correlation between the current and the traffic, and that can give rise to negative response. So this is what happening here, and there are some experimental situations here. And if there are questions, I can. So thanks to Amit and Urna who were involved in this talk. Amit is looking for a posted position now, and thank you. So if there are questions.
Is there any connection between this and some old work either by Deepak Dhar or Mustansir, or both on particles moving on disordered networks in which at some point when you increase the field, these things get pushed against a wall and therefore they slow down?
There was old work on percolation lattices. So there's a disordered percolation lattices, you can see negative response. But this was not an exact solution. I think there is no exact solution there. So this is a mechanism which I'm supposed is not on the model.
Pradeep, how is it different from some very old effect called gun effect?
I do not know what is gun effect.
Oh, you do not know? Please look at it.
Okay. No, but effect is same. I'm just saying that all I know is that we do not know how to calculate current in a non-equilibrium situation. Okay. We are not using Kubo formula. You need some exact formulation, because as long as you use Kubo formula, you live in the linear response region and it is always positive. So, I don't know any old work which can actually talk about current in non-equilibrium systems. Any other question? Abhishek, yeah, please. Okay.
So the response you calculate for currents, dj d epsilon equal to fluctuations. So non-equilibrium, I mean, for current it is not guaranteed. I mean, how to derive it? dj d epsilon equal to
No.
any analogy to
The models which I talk about, there I can directly calculate J as a function of epsilon, differentiate it.
and you get variance in current?
Yes.
I see.
Not variance, not a variance in the current. dj by d epsilon you directly get. That's what you need. Whether that is same as J square epsilon or J epsilon, that's not true. That you cannot calculate. Okay. But this two particle random walk is a very nice problem. Please do that. Yeah, please.
We can continue the discussion during tea. So thank the speaker again.